Okay. Yeah, in today's class, I will start with the idea of modulator that I had introduced in the last class. Right? Modulator in a block diagram wise, we can think of it as this, that it is there is a input to modulator is some voltage. Since it is in the controlled, it is not the voltage as a power, um, but it is not a voltage in reality as we see it, which is capable of doing some work, transferring some energy related to power, but it is a voltage as a signal. It is within the broader control system of the drive. So it is a voltage signal. So similar, but I am still writing it as voltage Vm. That is the voltage, and then there is a thing called frequency. Frequency, I am writing it as omega, omega. Let us say s, omega s. So this is the signal, that is the input to the modulator, and the output should be some kind of discrete signals, right? Some kind of discrete signals. So some kind of signals like this, high low discrete signals. So the input is a continuous function in time, continuous in time, continuous in time, but this is discrete in time, right? So this is the change that has to be done um, because of what reason? Because this will be the signal which will be given to the semiconductor devices, which can be IGBT, after probably amplifying it. Yeah, here it is amplification of that is done in gate drive, but gate drive is nothing but a kind of amplifier at the gate level, because gate signals may be at the level of 15 volt or etc. But the essential information is contained in this, in the modulator signal, that what we intend to do. And what we intend to do is that we want to switch, and we want to switch the semiconductor devices. And the objective of that switching the semiconductor devices is to synthesize a voltage, which is a continuous function in time. So this Vm is that continuous function, and in electric drives, in AC drives, this Vm is generally a sinusoidal function. So Vm is equal to some magnitude V capital M sine of omega st. A kind of continuous signal that we see, that is the input to the modulator. Obviously omega s is involved in it, and then correspondingly we need to generate some discrete signals, discrete in time. You must understand that discrete in time signals, which will be used for driving the semiconductor switches, which may be IGBT, which may be an IGBT, or which may be a MOSFET, such kind of semiconductors would be driven by these gate signals. So why I just want to remind you that why they are not continuous, why VM cannot be directly given to the gate of these semiconductors even after amplifying. The reason for that is that we don't want to operate the semiconductor devices in the active zone. We really want to operate them in the saturation zone. That means we don't want to operate them as a switch. So what does it mean when I want to operate as a switch? By switch I mean when it is either fully on or fully off. Fully on meaning that the voltage across the semiconductor device is 0. That is a fully on state. No voltage drop across it. But at that time there is current through it. So what is that happening? If we look at the semiconductor device, there is no voltage across it in the on state, but there is current through it. So there is no power loss in the semiconductor device. Similarly, in the semiconductor device, when it is off, then we have full voltage across the voltage, full system voltage is appearing across this, but current is 0. V is equal to Vs, V device. If I call it V device is equal to system voltage Vs, and the current is in the off state, the current is equal to 0. So power loss in the device is equal to 0. And the on state, as I said, then on state V device is equal to 0. V device is equal to 0. And the current, this is current, I device, and in this case I device is equal to anything. It could be whatever the load current, whatever the system current. I will say S. S implies suffix is implies system. That means the requirement of the load, requirement of the voltage and current system of the in which these switches are used. So this is what we know, define it as. So first let me write it that P device is also 0. So this is what is known as switched mode operation. Switched mode operation of semiconductor devices. Objective is to have no loss in the devices. No loss. Objective no loss in the semiconductor devices. So we cannot afford to have any loss in the semiconductor devices because we are just processing the power. We are not consuming the power. The drive system, the drive semiconductor power converter system of the drive is not supposed to consume any power. It is supposed to process the power. That means power wise it is supposed to make the output power equal to the input power. It cannot afford to consume it because if it consumes then the efficiency becomes less. So with this objective in all electric drive systems, for that matter any power electronic system, the switches are operated in these two modes only. These two modes in the VI plane. In the VI plane, if I see I, this is I and this is V. It is either operating here in the on state. This I current is determined by the load. Okay, it is not, it could be anything. Theoretically, it could be anything till it crosses the rating of the switch. But it depends upon, at that moment, it depends upon I is equal to I system or I load. Okay, and V is equal to voltage across the device. When this is in the off state, it is blocking the voltage, and however the current is 0. This is the current is 0. This is the off state, and then V is equal to Vs, system voltage. Okay, so you see that it will either in the on state it will operate here, and in the off state it will operate here. Not only that, I am not mentioning here, and I am not talking about it. When he has to do for go for any transition from the on state to off state, it has to go along the axis like this. You see that on to off, it has to go from certain current to blocking certain voltage. How does it go? It's during the transition. When it is moving from on state to off state, it has to first reduce the current and then move along this axis, along the voltage axis, along the voltage. Voltage is then supposed to build. If it tries to move in any other path, it will encounter loss. Suppose it goes in this path, then during the transition there will be a loss within the device. Loss within the device. So its transition path trajectory is also on is also aligned to the x and y coordinates. And this is how it will move. Off to on, it will then off to on, the voltage is there. So first voltage has to collapse and then current has to build. So this is the switching trajectory of the would be the switching trajectory of the devices. The whole objective is to reduce loss within the semiconductor. Okay, and that is what we call soft switching. When that thing doesn't happen, we call it hard switching. Okay, but at least soft switching, hard switching is a little difficult aspect of it, because you have to control the process of change. We have to control the process of transient, on to off and off to off. That is a difficult thing, but at least this could be ensured that in the on state there is no loss in the device. In the off state there is no loss in the device. It doesn't mean it is not doing anything. On state it is doing a very important thing, that it is passing the current. In the off state it is doing a very important thing, that it is blocking the voltage, not passing the current but blocking the voltage. So this manner, when these things happen in this manner, we see that the reasonable and conduction loss is and the blocking loss, at least theoretically, is equal to 0. But never it will be like that. There will be slight voltage drop during the conduction state and slight blocking loss based on the leakage current. There will be slight blocking loss in the off state, but those are insignificant. So first, so this is the reason why we want discrete signals from the modulator. Modulator cannot give continuous time signal at this output here. It cannot give any continuous time signal. It has to give a discrete signal. So this job has to be done by this. But it cannot be just like that, any arbitrary discrete signal. You must understand that it must somehow represent the original continuous time signal. And most often in electric drives, in AC drives, this continuous time signal is a sinusoidal signal of certain specific frequency, and it has a certain as a sine wave, it has a certain magnitude, right? It's a certain peak value and certain this thing. And how the peak value is obtained and this frequency is obtained, we have got in the last class. We have got in the last class that this omega s is actually the synchronous speed. Synchronous speed in electrical terms. That means after multiplying it by into p by 2, omega c into this omega s is nothing but, in last class if I want to relate it, then I'll say omega c into p by 2. P is the number of poles. That is how we will be getting it. And Vm is obtained from the V by f curve. There was a V by f curve I had drawn, that given this frequency we always need to maintain a certain amount of voltage as per a straight line curve relationship between the two. So that will be the requirement of the voltage. So that point, that will be the requirement of the voltage value. So let us say that will be the corresponding Vm, and then Vm sine omega t will be the actual time function of the modulating signal, right? Right. So you see that this discrete signal has to represent a sinusoidal signal whose peak value we know, and whose frequency we know. So you must understand that discrete signal is one way much easier to do. Suppose somebody tells me to generate a sinusoidal signal from another sinusoidal signal of different frequency and different voltage magnitude, then I will struggle to do that. What I mean is that suppose I tell you that I am giving you a sinusoidal signal and generated another sinusoid. So it's not that it is impossible. Suppose I say that I'm giving you this kind of sinusoidal signal, but now you generate a double frequency signal. Suppose I say that you generate a double frequency signal. It will be difficult for you to generate it. It will be difficult for you to generate. Suppose I say double frequency signal whose magnitude is also half. This is the original magnitude. Let us say this magnitude was Vm1, and I am asking you now to generate another voltage, which is Vm2, where Vm2 is equal to Vm1 by half, and this is the frequency. Frequency-wise, also it is half. This is omega s2, and original frequency. The time, it should be time, otherwise time, it should be time t2 corresponding to this, and the it is not t2, t2 is here. T2 is the full period, t2, and initial original thing was, let us say, t1. So it will be extremely difficult to generate. You feel that. You can understand that such an electronic circuit is not easy. Given one sine wave of certain frequency and magnitude, you are generating precisely half the magnitude and half the frequency. So that is not so easy to generate. In one way, discrete signals are easy to generate. Discrete time signals will be easy to generate. But because what we will do is we will apply the principle of averaging. I will tell you that. So how do we apply principle of averaging? Let us take that original signal conceptually first. First is that I know what signal I need to generate. Suppose I know, right, in the original sine form. Suppose I know this signal I have to generate. So then this is the signal. I am just writing it as V small m is equal to Vm sine of omega st. Let us say this is the signal I have to generate. What my idea will be to do some kind of, to break it into small equivalent magnitudes of voltages. What I mean is that you break it into small periods, like this. As small you can do, as accurate it will be. So this is what is known as the total period. If original period corresponding to that, if I define as t, the small periods I am defining as ts. Obviously it is continuous. You understand that it is continuous, dot, and this side dot. So this small period I am identifying this as ts, right? So in the ts period, what I will do is I will make an approximation. Approximation is that in this time the original sinusoidal signal is not changing much. Why? Because I have chosen ts to be very slow, very small than t, very smaller than t. So in this small time, I will not assume that the things are changing much. I will say that they are like sample values of the signal. That means I am conceptually thinking like that. At the kth instant, kth sample, this voltage is Vmk is equal to Vmk is equal to Vm sine into k into kth value is k into ts at that time instant when t is equal to kth sample value. This is the kth sample value, kth sample. After that, within the period there is no change. We think that this voltage is not changing within this sample period. This value is then frozen constant. Its value is, it is now Vm sine of k ts. T is at ts, it is this thing is kth sample. This time is ts, and this is at the kth sample. This is during the kth sample, right? So we may assume that provided we have a very high switching frequency, ts small means switching frequency is very large. That means I say that fs switching frequency is very large compared to this I am confusing this thing compared to, let me write it as this way, 1 by t. 1 by t is the frequency. The switching frequency is fs. So switching frequency is also equal to the sampling frequency, in which we will be considering these two signals and make an equivalence of it. So I accept that the values are changing sample by sample as we change k from 0 to 1 to 2 to 3 to 4 and etc. Let us say k value is, let us say I am just taking k is equal to 2000, maximum k max. Shall I write it this way? I will write it this way. I will say that k as a sample number varies from 0 to 1 to ... to 1999. Let us say these are the number of samples. 0th sample being here. This is 0th sample being here, and this is being the, let us say, kth sample. 0 and then 1, then 2, this thing. So within that small period, this modulating signal, this signal we will name is that modulating signal. This name of the signal we will call it modulating signal. Modulate, T-I-N-G, modulating signal. The actual voltage we want to resemble like this, not resemble in shape. We are trying to make it resemble in average. So actual, this is the actual shaped waveform. We are very sure that we cannot produce the actual shaped waveform, but we would like to have produce a switching waveform whose characteristics would be mimicking or would be representing the sample value of the modulating signal at that specific sample instant, right? The sample instant is kts. Yeah, at that sample instant, and in that kts duration, I am not thinking that the voltage is varying. So in essence, I am thinking that the signal is like this kind of discrete steps. It is consisting of discrete steps. It is not a continuous valued signal. It is discrete steps. So the discrete valued signal, which is not changing, that will be made equal to the switching waveform. Now we are changing the signal completely from a continuous time signal. We are going to produce a discrete time signal. That discrete time signal's average value will be equal to this sample value. That is what is the equation we want to ensure. Okay, so so this is what is the objective, right? I may even write it this way. That this modulating signal in the kth sample thing. So I can write it this way, that since it is equal in average sense, so let me write it this way: 1 by ts, 0 to ts, Vmk dt, this is the average value of the signal, is equal to the switching signal I am producing, that's average value. So 1 by ts, 0 to ts, V switch, That means it's a continuous signal, two discrete signal I am producing, but its average value are equal. So this into dt, they will be have to be equal. Right? Now, look at this. Conceptually, this signal has to have positive and negative values. VMK could have positive and negative values. Okay, switch, SWITCH, V switch, right, right. So this is a continuous time signal, okay, continuous time signal. Therefore, but its values can go to positive and negative. Since it is a sinusoidal, it is actually mimicking a sinusoidal signal. So these values VMK in some sampling instant it will be positive, and some sampling instant it will be negative, right? Therefore, in the switch part, we need to have both positive and negative values. Okay, the switching should be such that it can produce maybe constant valued, but positive and negative value, right? That must be the requirement. Otherwise, I cannot represent a signal which goes plus values, which goes positive and negative. So from that concept, let us TS doesn't matter, right? So VMK is a constant during the sample period KTS. So I can write it. This integration is simply VMK into TS. This integration. But what about this integration? This integration, since it is a discrete signal, and for some time it is positive valued and sometime it is negative valued. Sometime when it is positive valued, we call it the on time, T1 time, on time of the switch. And when it is negative valued and when it is off, it has to be a negative value, because the modulator should have the ability to give both positive and negative valued signals, signals. But this, therefore, this is due to switching, it is breaking into two parts, 0 to T1, where T1 can be thought of as on period, T1 can be thought of as on period, okay, and TS minus T1, therefore, should be thought of as off period. Okay, here all the time you note that VMK values would be changing, continuously changing in sample by sample, in sample to one sample to another sample. But here we have two frozen values. One is plus VDC by 2 and another is minus VDC by 2. That is what, because we cannot afford to have many levels of voltages in the modulator. Okay, we cannot conceptually have many level of voltage, but we should have one voltage level. But using switching from that voltage level, we should create its positive version and negative version. We are thinking that positive version is created in the on period, that is the period during 0 to T1. And for convenience, I am writing this label. The total voltage is VDC. I have broken it into two parts, so therefore I am writing it as VDC by 2, right? So VDC by 2 during on time, right? And the remaining part of the thing would be this thing. So it is T1 to TS. Ability to deal with positive voltage, but do not have the ability to deal with any, do not have any negative voltage, then I will not be able to do this. So in the switching period, I am using for some time VDC by 2 voltage and sometime minus VDC by 2 voltage. Why I am writing VDC by 2? Because the here also I am doing some practical aspect of it. What I am trying to think that I have a at such one voltage level VDC, okay, as such I have one voltage level. Nobody has given me explicitly a negative voltage. So what I am doing it, I am breaking, I am conceptually doing it, dividing into two parts, maybe using a capacitor, and taking this middle point as the reference. Reference means reference voltage, middle point voltage. Assuming that the capacitors are equally charged, okay, so therefore they have broken into two parts, VDC by 2 and plus and this one I will call it minus VDC by 2. So this is how from a practical voltage level of VDC I am generating one positive voltage and one negative voltage by breaking this voltage into two equal halves. Maybe using a capacitor, we are breaking it into two equal halves, or maybe conceptually you may think that the voltage VDC itself is consisting of two batteries, where somehow you have got the center point of the battery. Okay, in real life we will be having this kind of capacitor split. The capacitor middle point will be thought of as the reference voltage or zero voltage. This is how we will be getting getting both positive voltage and negative voltage. So this is the level of voltage. Okay, how do I get a switch voltage? Switch voltage is here. Let us think that this voltage, this point with respect to the reference is switch voltage. Let me write switch voltage here. This is the switch voltage with respect to this node, with this node and this node. This voltage is switch voltage, right? So this voltage, switch voltage, why? What it means? It means that if the switch is on, you can clearly see that if the switch is on, then this switch voltage becomes, this is on actually. This is on, and when this switch is on, the voltage that you are getting, V switch is equal to VDC by 2. When the switch is off, okay, when the switch is off, this switch, this is the main switch Q, and they are complementary. None of them can be on twice together, because that will short circuit the voltage source. So that is not allowed. So if Q is off, implies that Q bar is on, and the moment Q bar is on, okay, you will be getting V switch is equal to minus VDC by 2. Right? This is the real life how this signal has to be, the two levels of voltages have to be generated, where you are basically shifting the reference. Instead of using this as the reference, you are thinking the center point of the capacitor, two capacitors that are connected in series, is your reference. This is how from a unipolar thing you are able to create a bipolar voltage. Okay, nothing great. I can always say that, suppose I have been given a 10 volt, I can say that with respect to a middle volt, if I 10 volt, I think of it as two 5 volts in series, 5 volt in series. Then with respect to this point, this voltage is +5. With respect to this point, this voltage is -5. So nothing exceptionally new or anything. It is just shifting of the reference. The reference is not shifted with here, shifted from here to the center point. Right? So this is how the actual switch will work. But in the modulator is essentially, we are generating this idea of how long this switch Q1 has to be on, how long the switch Q has to be on, and how long the switch Q bar has to be on. By we are determining that. There all the things are dealt with in a signal level. Okay, so so this is the equation, but ultimately this is the equation that we need to satisfy. So let us write the equation in a clean manner. So in a clean manner, if we write the equation, what we get is VMK TS in a discrete way, VMK TS VDC by 2 into T1, right, minus VDC by 2 into TS minus T1, right. So what we get then, is, let us define a new term. T1 is equal to D into TS. We are defining a term called duty ratio here. So our D is defined as T1 is equal to the on time is equal to D into TS. So then we can write right? Then we can write VDC by 2 into D minus VDC by 2 into 1 minus D is equal to this VMK, right? VMK or okay, let us write VMK itself. So I should have written VAC because it is in the actual physical voltage level. So it should have been written as VAC. When it will be represented in the modulator, that will be written as VMK. So I am saying that VAC is the actual AC voltage that needs to be produced. Actual voltage, and VMK is a modulating signal that represents that voltage. Is a modulating signal that represents it. Okay, so let me write it VAC because I am using VDC. VDC is the physical voltage. Okay, and so that's why I'm writing it as VAC. VAC sampled at that kth instant, you can think of, which is almost implied that VAC into K. VAC into K, not VAC into K, VAC kth value, VAC K, you can think it this way. So if I simplify it, then I get 2 into D into VDC by 2 minus VDC by 2 is equal to VAC, right? VAC K, right? So D is equal to then VAC K, kth value of that instant, plus VDC by 2 by VDC, right? So what we are getting is D is equal to half plus VACK by VDC by 2, right? Sorry, half VDC. Achha, sorry, this okay. So I can write it as, I can organize it a little differently. Half into 1 plus VACK by VDC by 2, right? Right. So it is nothing but I'm trying to show you that how the duty ratio will have to be varied. Okay, will have to be varied as per the variation in VACK. Okay, here VDC is a constant, There is constant level of voltage is given. What I am doing is that I am using this constant level of voltage, I am trying to produce a discrete signal that represents the sinusoidally varying signal. And what is the only variable I have? Since my label voltage is frozen, VDC is a constant, it's a label voltage, it is frozen, I cannot vary it. But I am trying to vary, I am trying to represent a time varying function, a sinusoidal in this case, and most of the power electronic cases, I am trying to represent it. So I must have a variation into the switch signals time period, right? And this time period is represented by a duty ratio, right? Because duty ratio is nothing but T1 by Ts. And we can clearly see that this duty ratio has to be modulated, because this is why the word modulation is coming, because the signal is sinusoidal. Therefore, to get a representation of this sine wave in the actual output, the duty ratio is also somewhat modulated like a sine wave. You see that VACK, it has a sinusoidal function. VACK in some instant, whatever the value, next instant the value is changing in the, as per the sinusoidal function, it is changing. So that is reflecting in the duty ratio function. But the duty ratio here is, in real life, it means the on time is to the total period ratio. The signal that is produced is like this. This is the signal that is produced. This is the on time. This is the on time, and this is the period Ts. So this on time is now modulated. That means it will change. It will continuously change. It will change. Never go beyond 1. Never go beyond 1. It will change from 0 to 1. This on time will be continuously changing, continuously changing, continuously changing to mimic this sinusoidal signal. Notice that VACK has positive and negative value, right? Let us say VACK at the maximum case, let us say VACK is equal to VDC by 2. Let us say max. When VACK is positive maximum, it is equal to VDC by 2. So then what is the duty ratio? Then the duty ratio is 1 plus 1, half of 1 plus 1, and is equal to 1. So when the modulating signal goes to its peak value, the duty ratio becomes 1, which is commonsensical. Which duty ratio becomes 1. This is the duty ratio which is becoming 1 when this goes. When it is going its negative minimum value or the negative peak value here, then VACK by VDC by 2 is now minus 1. So then what is the duty ratio? Then duty ratio is equal to 0. So D is equal to 0 when VACK is equal to minus VDC by 2, right? So therefore D is always varying between these numbers 0 to 1, right? In the case when you intend to produce from this thing a signal which is touching the level of VDC by 2, that means VAC is touching the level of VDC by 2. The VAC signal is touching max is VDC by 2. Don't expect that this thing can produce any voltage which is greater than VDC by 2. Don't expect that, because that requires that the duty ratio has to be greater than 1, which is not possible, which is impossible. So maximum value of VACK is VDC by 2. This is what is the maximum value. It can be less than that. It can be less than that, is not a problem. But then the duty ratio will vary over a smaller range. Okay. So so the maximum possible voltage that this modulator can mimic through the variation of the duty ratio is equal to, corresponds to a level of VDC by 2. Okay. Another interesting point you should note here. What is that another interesting point? You see that it has come as a ratio. It has not come as any physical values. It has come as a ratio. VACK is the physical value, VDC by 2 is a physical value, actual voltage, actual DC bus voltage, actual DC voltage with which you will be producing VACK at the motor terminal. Why I am saying it is a physical thing? Because this voltage has to be mimicked at the motor terminal. VACK has to be represented in the motor terminal by a time varying or the pulse width varying signal. Why I am calling pulse width varying? Because duty ratio is actually a variation of the pulse width. Time period is not changing, TS is not changing. So that's why this process is called PWM, pulse width modulation. Pulse width modulation. Because you can see that TS is constant. We are not changing any TS in the process. TS is constant, only D changes. D is the duty ratio, right? So that is a very that's why the word pulse width modulation is coming. Pulse width is always modulating, always changing as per the VACK that it has to synthesize through producing a discrete signal, discrete time signal. Okay, so that is what is there. It has only one variable now. Since the label has been frozen, you can never choose any value other than VDC by 2 and minus VDC by 2. In essence, the voltage level is only VDC. Okay, so you cannot go beyond that. So then you can only synthesize it by adjusting in terms of time. What is the criteria you are maintaining? That in that every small period Ts, there are many small periods, but every small period you are equaling their average values. The average value of VACK over that period is actually VACK. There is no difference in that, is VACK. So that VACK is now being made equal to the is being made equal to the duty ratio, is being made equal to the discrete signal whose labels are varying between VDC by 2 and minus VDC by 2. By adjustment of the time, or by selecting the time for which we will produce VDC by 2 and for which we will produce minus VDC by 2, right? So that is the philosophy of it, right? So philosophy of it is also giving you an interesting aspect of it, right? It is saying that the duty ratio signal, for the production of the duty ratio signal, I do not need the physical signals at all, because this is nothing but a ratio, right? So this ratio therefore can be created by some either low voltage level signals or even by a code, right? Actually it will be created by code in digital implementation, but let us think that now it is analog signal, which is that signal doesn't have to give any power. It has to be just maintaining this kind of ratio. So therefore we choose, in place of VDC by 2 signal level, we choose a signal a VT, a voltage VT. I will come to that. It is a triangle waveform or sawtooth waveform peak, and in place of VAC, we choose a signal V small m. This is the way. This is in the modulator level signal. Modulator signals. This is power level circuit. I will say circuit voltages, voltages. So I have to create a same ratio. If I can create a same ratio here, then I am done. I will be able to produce the duty ratio signal without using the circuit voltages into the relationship. This relationship can be created because it is proportional. VAC is proportional to VM and VDC by 2 is proportional to VD. If I take this concept, then VM by VT will also give me the same duty ratio that I have that I need actually in the circuit to create. So same duty ratio will be created by in the modulator by some signals such as modulating signal. Modulator, this signal is called modulating signal. And this is called carrier signal. CARRIER, carrier signal. This is representing the carrier signal peak, this VT, because VDC by 2 is a constant, so therefore VT has to be a constant. This is the carrier signal peak, right? So let us see that how in the modulator the same equation I can generate using in terms of VM and VT. I have to generate this same equation in the modulator, but I cannot use VACK and VDC by 2 because they are high voltage things. They are circuit voltages. I cannot bring it into the control system. My control system always works in low voltage. Either if it is a analog control system, we are using op amps. They are low voltage. We are going only up to plus minus 5 voltage. If it is a digital control system, it is even lower, because that is then after ADC conversion, these voltage levels are becoming just numbers, right? So I am not, I cannot generate duty ratio using the physical world variables, the physical world voltages. I have to have a representation, and that representation is the modulating signal, which is replacing the actual AC voltage, and the triangular peak, which will be representing the DC bus voltage, right? Just let me draw it first. Right. So let us first draw a waveform like this. Right. Let us first draw a waveform like this, where the modulating signal is here. Okay. Must understand that the zero of this line is here. So this is Vt, and this is Ts, and this level is modulating signal. Okay. So what do we see? We see that there is a sawtooth. This generation is this waveform shape is called sawtooth. Sawtooth. It is actually representing a variation that as the time is varying, this is also varying. It is a proportional to time, because duty ratio is at that specific time the objective is fulfilled. So it is like a graphical solution. I do not know initially at what point it will be solved, but I have to give a representation of the time. And this signal, this sawtooth, is the representation of the time as time is changing. In this small Ts period, when you are looking at it, the time is changing like this. Time is increasing. So we, depending upon the value of the modulating signal, the solution will be obtained that at that specific instant the modulating signal and the modulation signal average becomes equal to the switched signals average. That is what it will be done. Okay, so it is done by these two signals are compared, and you generate a kind of duty ratio signal. Duty ratio means on and off signal, discrete signals ultimately. This is a discrete signal that you are generating, on and off. Sorry, I should do it from here, like that. Right. So in the beginning, you don't know. So let the time flow. Let this increment happen linearly. And at this instant, Vm is becoming value equal to that, satisfying the time relationship. Because after that, this is zero. This is zero or negative. Zero means it is off period. This is the on period. This is the on period, and this is the off period. Okay, and you are trying to solve it graphically. You are just solving it graphically. That at what instant the criteria that you have set happens. Okay, in the beginning you don't know. So let the time flow and they let them intersect where the averaging criteria is fulfilled. You must understand that in this small Ts period, Vm is as such not varying. Vm is varying in a slow manner. It is varying with respect to the time period T. T is the sinusoidal signals time period. But in this small time Ts, which corresponds to the switching period, which corresponds to the comparison period, where the modulator is comparing, okay, modulator is comparing many times in the total time T. Okay, so in this small thing, Vm may be assumed to be constant. Vm is assumed to be, the modulating signal is assumed to be constant. So by looking at it, we can write this from the similar triangle principle. We can write this, right? This is one triangle, and another, there is another bigger triangle. This is another bigger triangle. This is a bigger triangle. So from the similarity, these two are similar triangles. So we can write it that Vt minus Vm divided by 2 Vt, right? Vt minus Vm by 2 Vt is equal to Ts, 2 Vt, because Vt has been taken as this. 2 Vt is up to this. From here to here is 2 Vt. 2 Vt by 2 Vt is equal to Ts minus, Ts is the full period, and this is dTs. This is considered to be dTs is equal to T1, which we had used earlier. dTs minus dTs by Ts is equal to 1 minus d, right? So here we get half of 1 minus Vm by Vt, right? Half of 1 minus Vm by Vt is equal to 1 by d, equal to 1 minus d. So I get that 1 minus Vm by Vt is equal to 2 into 1 minus d. So I get that Vm by Vt is equal to 1 minus 2 into 1 minus d, right? So is equal to 2d minus 1. So I get d is equal to half of 1 plus Vm by Vt. So you see the same relationship we have obtained as we require in the actual physical circuit. Actual physical circuit relationship we have shown that this is the relationship we want. Actual physical circuits relationship we want. Instead of using VACK and VDC by 2, if we represent VDC by 2 as the peak of the triangle waveform, triangle, not triangle, sawtooth waveform, this is called a sawtooth waveform, then we can obtain the same duty ratio relationship that we would be requiring to synthesize the voltage Vm using discrete signals, using discrete voltages, right? So this is what is the modulator doing. Modulator is actually scaling the things from the power level to the control level signals, from the power level voltages to the control level signals, and ultimately what is meaningful here is the on time or off time. That is what is the meaningful information that a switch requires. Switch doesn't require anything else. So actual semiconductor switch requires only on time and off time, which is being now provided by the modulator without dealing with any one of the high voltage signals, without dealing with the any circuit level quantities. I will not say signals, circuit level quantities, voltages, right? These are signals. So how do we do it? We generate a sawtooth waveform and compare with the modulating waveform. The modulating waveform has, in every switching period, is approximated to be constant, but subsequently it will vary. It has slow variation. So therefore, within the switching period, this is what is within the switching period. Within the switching period, don't consider that it is varying. It is remaining constant. And with that thing, we can get a duty ratio relationship that we require. Okay. Now, a small trick people sometimes play. You can see that subsequently, in the subsequent cycle, this is the cycle number 1. If we go to the cycle number 2, and assuming that this cycle is almost also identical to the voltage level Vm is almost identical here. Vm, let us say it is Vm value wise Vm1, and this value is Vm2, and assuming that it is almost same, 2 cycles almost same, then what we can do is that we can reduce the number of switchings that we will be requiring. Because here you can see that the number of switchings are required are 2, because here again another comparison will be done, and there will be producing the same duty ratio, but there will be 2 switchings. 2 switchings means, you see, 1 on and 1 off is 1 switching of the device, and then again 1 on and again 1 off, there's second switching. However, the trick is that instead of that, if you just use a triangle wave signal, that means you flip it like this, flip it, and then you generate a signal like this. By comparison, again by comparison, you are generating a signal like you are combining 2 off periods together. Basically, you are combining 2 off periods together. This will be combined together. This, and rest of the thing is on period. So here, so now you see that there are only 1 switching. This is 1 switching and one turn off and 1 turn on switching that would be happening. So in reality, actually we use this kind of triangle waveform as the carrier. This name is called carrier. Carrier is a high frequency signal because it has a frequency of what? 1 by TS, which is nothing but the switching frequency. That is what is defined as the switching frequency. Why that is what is defined as switching? You see, because one on, one off, and one on would be making one switching. So that's why the carrier waveform is generated carrier waveform is generated as a triangle waveform, which modulator has to generate high frequency triangle waveform, and the frequency is related to the switching frequency of the semiconductor devices. Vm is a sinusoidal signal, which is nothing but the a scale version of the actual voltage that you need to produce, but it is only conceptual. It is only in a signal level. It is not a physical voltage. It is only representing the actual voltage in the control part, in the digital or analog controller, in the control part, not in the power part. So this comparison is done there, and the duty ratio signals are produced, that these duty ratio signals are interfaced to the actual switching devices through a gate drive circuit. That is the whole picture. Okay, any question? Okay then, some question? Okay, okay then. Thank you. I'll stop here.